Every time you board a plane, you step inside one of the most sophisticated machines humanity has ever built. Carbon fiber airframe. Fly-by-wire controls. Engines generating over 100,000 pounds of thrust. GPS, satellite communication, real-time weather avoidance systems. And yet, the plane you board today crosses the Atlantic at almost exactly the same speed as a Boeing 707 in 1958. Both hover around 900 kilometers per hour. Your grandparents flew at the same speed you do. The 787 Dreamliner, 903 kilometers per hour. The Airbus A350, 903 kilometers per hour. The A380, 903 kilometers per hour, basically unchanged, not for a decade, for 6 decades. Meanwhile, your smartphone is about 1,000,000 times faster than the computers that guided Apollo 11 to the moon. Cars are faster. High-speed trains now run at 350 kilometers per hour. Medicine, computing, shipping, every sector shows dramatic advances. The commercial airplane. Frozen in place. By the end of this video, you'll understand exactly why. The answer involves physics, fuel mathematics, a wall in the sky called wave drag, and a sonic boom problem that no one solved. There was one exception, a narrow silver aircraft that broke this rule for 27 years. And the story of why it failed explains everything. When people ask why planes haven't gotten faster, 3 answers come up immediately. First, safety. Modern aircraft don't fly faster because traveling near the speed of sound is inherently dangerous. This collapses when you look at the record. The Concorde cruised at Mach 2, more than 2,100 kilometers per hour, for 27 years of commercial service. British Airways and Air France operated it across the Atlantic with exceptional reliability. Safety was not the barrier. Second, engines haven't improved enough. This is flatly wrong. The GE9X engine powering the 787 produces over 105,000 pounds of thrust with dramatically better fuel economy than anything from the 1960s. The engine is not the limitation. Third, air traffic control can't manage faster aircraft. ATC systems have successfully adapted to enormous increases in traffic volume over decades. Handling faster aircraft is a solvable problem, not the fundamental barrier. None of these answers survive close examination. The real answer is in the physics of air itself, specifically, what happens to airflow around a wing as it approaches the speed of sound. Sound travels at about 1,225 kilometers per hour at sea level. At cruising altitude, it drops to 1,062 kilometers per hour. Commercial aircraft cruise at 900 kilometers per hour. That is Mach 0.85, 85% of the speed of sound. At this speed, a wing generates lift by forcing air to accelerate over its curved upper surface. At Mach 0.85, the aircraft is below the speed of sound, but the accelerated air over the wing may already be touching or exceeding Mach 1 locally. When air exceeds the speed of sound in those local zones, it creates a shock wave. And shock waves create a catastrophic form of drag called wave drag. At ordinary subsonic speeds, drag increases with the square of velocity. But push into the transonic zone and wave drag adds a spike on top of that. Engineers call this threshold the drag divergence Mach number. For most swept-wing commercial aircraft, that threshold sits between Mach 0.85 and 0.88. Modern jets are deliberately designed to fly at exactly this edge, not beyond it. The swept wings on every jet airliner, angled back 25 to 35 degrees, are not decorative. Sweeping the wing delays the point at which local airflow goes supersonic. The precise wing profiles on modern jets, supercritical airfoils, were developed in the late 1960s by NASA aerodynamicist Richard Whitcomb. Their flatter upper surface distributes pressure more evenly and delays the shockwave onset. Without them, modern long-range jets would not be economically viable. All of this engineering aims at one goal: get as close to Mach 1 as possible without triggering the drag increase that waits just beyond. At Mach 0.85 to 0.87, an aircraft achieves the sweet spot. Push to Mach 0.90, and fuel cost climbs sharply. Push to Mach 0.95, and the economics collapse. This physics ceiling has held for 60 years. Now let's put numbers on this. A 787-9 flying London to New York, 5,500 kilometers, burns about 60,000 liters of fuel at Mach 0.85. Push to Mach 0.90, just 5% faster, and fuel consumption rises 10 to 15%. That is 6,000 to 9,000 extra liters per crossing. At current jet fuel prices, $5,000 to $8,000 in additional cost per flight. In exchange, you shorten the journey by roughly 20 minutes. Airlines run this calculation constantly. Passengers will not pay meaningfully more for 20 fewer minutes on a transatlantic flight. The math never closes. Now take the calculation fully supersonic. At Mach 2, wave drag is enormous. Air friction raises the aircraft's skin temperature significantly. The Concorde's frame used aluminum alloys and titanium engineered for this thermal stress, heavier, more complex, far more expensive. The Concorde burned 4 times more fuel per passenger per kilometer than a comparable subsonic aircraft. It carried only 100 passengers, versus 400 or more in a standard widebody. The model only worked on London and Paris to New York routes, where passengers would pay the equivalent of $10,000 to $12,000 today for 3 hours instead of 7. When the Air France Concorde crashed near Paris in July 2000, the entire fleet was grounded for over a year. Many wealthy passengers discovered during that gap that 7 hours in business class was entirely acceptable. Bookings after the 2001 return never recovered. The retirement in 2003 cited falling demand and rising costs. The crash was the trigger, not the cause. The underlying economics were always fragile. And the fragility had one source: physics. Beyond fuel cost sits a second completely separate barrier. The sonic boom. When an aircraft exceeds Mach 1, it generates a continuous Mach cone of pressure waves trailing behind it. This is not a single explosion heard at one moment. It is a sustained carpet of overpressure following the aircraft's entire path across the sky. On the ground, a loud sharp bang like an artillery round. Windows shatter. Walls crack. In 1973, the FAA formally banned supersonic flight over American soil. Most of the world followed. The Concorde was allowed to exceed Mach 1 only over open ocean. Its routes were precisely designed so supersonic cruise began only after leaving the coastline. This means a supersonic aircraft can only deliver its speed advantage on transoceanic routes. Transcontinental routes, New York to Los Angeles, London to Tokyo, are either banned entirely or require extreme ocean detours. That is a small fraction of global air travel. Put the physics ceiling and economic reality together and a remarkably stable outcome emerges. Every aircraft manufacturer, working independently, converged on the same number. Boeing 707 in 1958, Mach 0.82. The 747 in 1970, Mach 0.85. The A300 in 1972, Mach 0.82. The 747-400, Mach 0.85. The 777, Mach 0.84. The A380, Mach 0.85. The 787, Mach 0.85. The A350, Mach 0.85. 6 decades of competitive design, same answer. Not from coordination. From physics determining economics determining outcomes. The enormous progress in aviation went somewhere else entirely. Modern engines burn 50 to 70% less fuel per passenger kilometer than first-generation jets. The 787's composite airframe is lighter and stronger than aluminum. Safety record dramatically improved. Avionics transformed. But speed? Unchanged. The barrier is so stable, so embedded in industry economics, that it is almost never discussed publicly. Airlines know it. Manufacturers know it. Regulators know it. Passengers almost never think about it. And so 900 kilometers per hour on your flight tracker became invisible background noise. In the last several years, something genuinely new has appeared on the horizon. Boom Supersonic is developing the Overture, 65 to 80 passengers at Mach 1.7 on transoceanic routes. United Airlines and American Airlines have placed orders. A smaller demonstrator, X-59, completed its first supersonic flight in 2024, reaching Mach 1.1, the first privately built aircraft to break the sound barrier. Boom claims the Overture will operate at economics comparable to current business class fares, betting on modern engine efficiency and sustainable aviation fuel. Whether this holds at production scale remains deeply uncertain. The history of aviation is full of supersonic programs that looked promising and did not survive. The Boeing 2707 was cancelled in 1971. The Soviet Tu-144 flew just 55 scheduled commercial flights before being withdrawn. NASA is pursuing a different approach. The X-59 QueSST, quiet supersonic technology, is designed to produce a fundamentally softer sonic boom. Its elongated 30-meter nose spreads shock waves over a longer distance so they arrive at the ground as a gentle low-frequency thump, not a sharp crack. NASA plans to fly it over U.S. cities and present community response data to the FAA and ICAO as the basis for reconsidering the overland supersonic ban. If that ban were relaxed even partially, the economics of supersonic aviation would transform overnight. The next time you check a flight time, 8 hours, 12 hours, understand what that number represents. Not simply distance. The result of a bargain struck between physics, economics, and regulation, negotiated in the early 1950s and held almost unchanged ever since. Every optimization since made aircraft cheaper, more reliable, more comfortable, more fuel efficient. But not faster. Not from lack of imagination. Because the physics of compressible airflow near Mach 1, combined with the math of fuel cost and the politics of the sonic boom, drew a line at 900 km per hour that has proven economically impossible to move. New programs may challenge that line over the next decade. Or the line may hold for another 60 years. If this kind of analysis is what you want, subscribe. More is coming.